Fantastic. Such a pleasure to be back doing this conference on AI and science. So, welcome to everyone. And thank you, Margot and Tom, for really supporting us through all this. And we are looking forward to an exciting next 2 days. I also want to thank my ops, my co-organizers, Becca at U Chicago started this in 23, and it's been such a great partnership between the two universities to bring this initiative together, and almost a unique one because there's already been a lot of synergistic efforts. You'll see faculty not only from Caltech and Chicago, but also other universities really pushing forth the collaborative mindset that is essential to have success in this AI and science coming together. And many of these, the organizing committee are also around here. They'll be chairing the session. So I really hope you get to thank them when you meet them. So just briefly, like I want to start with the history, right? We always look back to look forward, and so many of you may not be aware that a lot of the rich history here at Caltech can be traced back to the roots of AI itself. This notion of interdisciplinary research is not new to Caltech. And in fact, the course that was started in 81 by Richard Feynman, Carver Mead, John Hopfield together, called physics of computation, right? So bringing together computation and physics together, they really saw those pillars to be essential. Hardware, right? Carver Mead is the father of chips. Of course, John Hopfield with neural nets and Hopfield networks, and Richard Feynman, of course, with the principles of physics. So all these need to come together, and the rest is history. And that also led um, towards the creation of the NeurIPS conference. I believe most of you, if not all of you, have attended at least one NeurIPS, and that's really the most well-known conference in the field. Last I checked, last year, I think there was more than 10,000 people. But to imagine that it started here at Caltech by Ed Posner and Abu Mustafa, who's still here at Caltech. So that really shows like the forward-thinking nature, and I'm really confident a lot of what is going to happen here in the next 2 days is something for the history books because there is so much of good energy and good ideas coming together. And that was really our goal as well when we started the AI and Science Initiative in 2018, right after I came here to Caltech. I was always excited about sciences, so I was almost like, oh, why didn't I go and study physics more? And here I had the opportunity to do all of that. And we've been doing this as a small workshop across Caltech every year. But now, thanks to the Chicago Caltech Joint Pritzker Conference, we are able to expand this scope and also the attendees much greater extent. And the first such event was held in Chicago in 23. This is the second one at Caltech, and the next one will be back in Chicago. And we already are going to announce the date soon about that too. So very excited to continue this year after year. So, the program, I won't get into it a lot more, but, as you see that we are trying to cover every area of science from biology, physics to neuroscience, health, climate, robotics. So we really want to show that span. And at the same time, you'll see from the talks the depth of what AI algorithms go into making this happen, right? So that's really, to me, the challenge is it's not just, oh, the AI is just all ready and let's just go apply it to science. It's not just AI for science, it's AI and science coming together because the development of AI algorithms themselves is challenged by the scientific problems. And that inspires us to innovate and think about not just the standard data-driven AI, but AI that truly works for scientific discovery. So with that, I really want to dive into that aspect, right? So we've seen AI become this, thing that everybody uses, everybody's aware of around the world. Most people know it as language models, but AI is much bigger than just language. And if we were to push this frontier of scientific discovery itself, how can we design AI to do that? Is language model sufficient, or do we need more than that? And so many people think AI scientists, where the language model can repeatedly go and look at scientific text and think about new ideas, can lead to new scientific discoveries. But as so many in this room know, ideas are just the beginning, right? And there are lots of good ideas, but the real bottleneck in science is the ability to go do the experiments, collect observations, all the hard work that is necessary to see if it works in the real world. And that's where just language is not enough, because textual knowledge is this high level ideas, but what really needs to be shown to AI is how the physical world works. And if you can model the physical world in all its complexity, then you have better hope to come up with this needle in a haystack, right? So the hay can be thought of as lots of ideas. What you really want is that one needle, the one great idea. And if you can have AI rule out all the bad ones and say this is the one that would really work in the real world before we build a big machine, before we go test this drug in the human trial, then we are in a much better place to have that bigger impact in scientific discovery itself. And with that in mind, the way I think about AI for the physical world is one that will understand different scales of interactions, starting from atomic scales, where if we want to understand how atoms in the molecule interact, to how proteins bond with drug molecules, and to going all the way to even planetary scales and asking, phenomena like weather, climate. Can we model that? Can we get an understanding? Can we predict extreme events early on so that we can save lives? So all of this is a hard problem because it's spanning so many different scales. Right. At the same time, unlike language models that had all of the internet to learn on, we don't just have this data sitting around. There's been many efforts to collect data, starting from molecular information to planetary scale information when it comes to weather and climate, but it's still never going to be of the scale that we see with text and images on the internet. And so if that is the challenge, then what else do we have? We have all of the mathematical theories, mathematical equations that are, saying how these different scales of interactions happen. So can we harness that in addition to data? And this is what I call physics informed learning, right? So it's not just data, the physics, to me, that could be partial differential equations, that could be laws of physics. How do we bring that together? And then adding that together could help us overcome the requirement of data. And it's not just about data being not enough. If we want to push the frontiers of discovery, by definition, that's something new, right? So that is not going to be present in the training data. So if you want to model a system, let's say much bigger than what was in the training data, it cannot happen just with a data-driven approach. We have to embed the laws of physics in different ways to enable this discovery to what I call extrapolate, right? So it's not just interpolating on samples that look similar to the training data. It's really going beyond and extrapolating and asking, can you make predictions on a system that is significantly different from what was in the training data? and be successful in that, have good uncertainty about the predictions you make, so that we can save the costs that of going to the real world, doing physical experiments, spending all of that time and money to see if it works. And so that's where it differs quite a bit from the standard language modeling approach, because we need guarantees about how well such a system would be in the real world. And so the neural operators as a concept that we've been working on really addresses this core issue that, you know, all the phenomena does not happen just in one scale or one resolution, right? To show you this point, like if you were to model like the uh, clouds here, so they're turbulent, they have these fast movement. If you just fix the resolution and then you zoom in, it gets blurry. So there is just not enough detail. If you say, this is the resolution I'm going to work on, and that does not resolve all the scales. So the flexibility of neural operators means you can keep zooming into any resolution and add more details of different kinds so that you fully capture that phenomena. And so that's where, for physical systems, having neural operators will help us think of them as a continuum rather than as discrete tokens. So when we think of transformer architectures for language, that happens, language is discrete, right? You have a fixed vocabulary and you model that. If you think about images that ChatGPT or these models produce, they have a fixed resolution. But as we see for physical systems, a fixed resolution is not enough because it does not capture all the complexity that is necessary just at that resolution. And so that's where this concept of neural operators means we now think of the world fundamentally as a continuous system. The weather is happening all around us, right? It's not just at discrete points wherever we observe, it just happens all around us, but we don't observe it everywhere. And so the input and output are these continuous functions, just that what we observe is a discretization of that. So we could observe our input at different resolutions, and we can also predict at various locations. For instance, I can ask, what is the weather here versus in Chicago? And so having that flexibility to have both the inputs and outputs on any locations means we can now take data at multiple resolutions. So you'll see in many climate modeling efforts, for instance, there's data available at multiple resolutions, right? So some simulations are cheaper to run because they're at lower resolution, but they're approximate. Then you have higher resolution data, but there's fewer amounts of that. And being able to combine all that together in one model, that's what neural operators enable, because we can seamlessly have any kind of data at any resolution be provided to it. And at the same time, the notion of physics informed learning, how we can add physics to the data, can be done by imposing the laws of physics. So you can say, I have observed my data only at these locations, so I can validate how well it's doing as supervised learning. But I also know that the physics between these grid points where I have no data should satisfy certain laws, right? So I can add physics laws in addition to the data laws, what we call physics informed neural operator. And we can do that at multiple resolutions. So this kind of multi-scale, multi-resolution learning is one that's really important to have very highly accurate prediction of physical systems, like how fluids move, how weather occurs. And that's what we've seen in a lot, many examples work very well. And I won't get into the actual architectures a lot, but the idea is, in order to enable this kind of learning at multiple scales, you can have a whole variety of different architectures. So every neural network that worked for language or image, you can turn also into a neural operator, right? The neural operator is really this umbrella under which you can model different systems. But at the same time, using ideas from applied math, from traditional simulations, such as using Fourier transform, has been very successful as well. Combining those ideas with nonlinear learning of neural networks has really paid off. And this is also a great example of interdisciplinary collaboration that happened here at Caltech, because we are not just in isolation saying, let's just borrow what has worked for natural images and text and apply it to science. Let's look at from the fundamental algorithmic level. What has worked well with traditional simulations, we take in those components. For instance, the Fourier transform means you're looking at the spectrum and you're naturally looking at multiple scales through that. And that's a great inductive bias in many examples. And at the same time, having nonlinear transformations means we have a flexible model that can be expressive, that can learn a complicated phenomena very efficiently. So I'll show you now success stories and examples where these neural operators have really taken off. One of the ones I've been really proud to see is in weather modeling. We built the first AI-based high-resolution weather model, ForecastNet. And what you see in this visualization is how it can capture the atmospheric rivers. So they are thousands of miles wide, and when we first you know, trained this model and saw how well it works, we were quite surprised because it's tens of thousands of times faster, but also accurate. And so it's not a trade-off. You're getting a much cheaper model to work as well as the traditional models. Because with traditional forecasting, what's done is physics-based modeling, right? So using partial differential equations, you try to solve that iteratively for each forecast, and it gets very expensive. It needs a big supercomputer to do that. Whereas our model has been able to run on a local gaming PC. So you just need a consumer grade GPU and it can run lightning fast. And we were the first to also permissively open source the model, and it's been used extensively by, companies, startups, weather agencies. The European Weather Agency has hosted our model more than 2 years now, and it's available to all weather scientists. And that really, to my surprise, the adoption from the weather community has been so positive, right? Because, there has been that challenge before that uh, this is not physics based, do I trust this forecast, to now, let's compare it side by side and let's see what these models are really doing. And they are many times even doing a better job than traditional models. As an example, Hurricane Lee from last year, this forecastnet a prediction that you see in orange was able to correctly predict the forecast of making the landfall several days earlier than the traditional ones. So it's what we call a missed forecast with the traditional models, and AI-based models were able to beat it. And that's the first time when also the mainstream media was very surprised and covered a lot of this, because we were able to not only be better in terms of speed. We are tens of thousands of times faster, but we are also able to beat in accuracy. And now the latest models are exceeding in all kinds of different accuracy metrics, and at the same time be much cheaper and faster. And so that's what, to me, AI and science coming together brings about, right? This ability to uh, exceed what we can do in terms of the current technologies. But the key was, okay, it's fast and it's democratized, so everybody can run weather models, but can it enable us to do better forecasts? So if you saw the title of my slide, it's really about pushing that frontier, right? What is the frontier with weather models and how do we push that? And to me, the frontier is really about extreme events. The most challenging ones are not predicting the weather here in California, where most of the days it's sunny. Sure, sometimes we also get the extreme events, but those are the ones where you cannot just rely on one deterministic forecast. So you see here the if you do one forecast, you could be quite wrong because it's what we call a chaotic system. So the butterfly effect is another popular term. And the idea is when the hurricane is forming early on here in the coast of Caribbean, you really can't tell what would be the exact trajectory of where that'll go. Right? Because there's also noise, we are not recording this with high enough resolution. And in fact, if you saw the Twister movies, that's all about improving the resolution of recording the conditions for these events. So, given that uncertainty here, what you really should be doing is not just making one prediction, making lots of predictions by appropriately adding noise to the current initial conditions and seeing where the trajectory goes. And you can see the trajectories can change widely depending on the noise you add here. But then you get a risk profile, right? You can count how many of these tracks hit a specific region, let's say in Florida. And then you can say, here the risk level, I have 90% chance of hurricane making landfall. And that's gonna have other implications like should there be evacuation. So what we really care about in such extreme events or the tail events is what are the probabilities. And getting those probabilities correct has been one of the north stars in weather modeling. And the reason why that has been challenging until now is, to me, one of the big bottlenecks is the computational cost. Right? I was very surprised that traditional forecasts use only about 50 ensemble members. So from statistics, we know if we only averaged about 50 values, that's just not enough to have a good confidence in terms of the outcome. And that's what we see with now AI-based models. Because they're so cheap, we can now have thousands of ensemble members. So we can really scale up this aspect of ensembling and getting to really precise statistical guarantees. And that's what we've done in the latest version of ForecastNet, which I'm very happy to see that we are not just doing well on typical weather events, but really being able to exceed on the extreme weather events like hurricanes and heat waves. And that has a lot of implications as we think about this increasing in intensity and frequency in the coming years. So I didn't go into all the details of what went into learning for the weather model. One great thing is there was lots of data available, right? 40 years of data available from the European weather agencies that was open source. So that really helped researchers like us to just go in and say, let's try this out rather than, having to collect the data. But it turns out that data by itself was not enough when we think about not just a short-term weather, but really long-term climate. So if we try to roll this out like I did here, and then this was a model that pretended that the Earth is a rectangle, which it is not, right? And this one incorporated the spherical geometry, and then you do the rollout, it keeps that long-term stability better. Of course, like as you will see in the talks tomorrow in the climate session, there's a lot of nuances of the small scales having to be correct to, and you have to run it long to get the climate simulations to be correct. So that's the challenge. And but for that, we cannot just do a data-driven AI. We have to add some notion of geometry and physics to really make these models work. Right. So that's when I think of this as a foundation model, because even though we trained it to predict only over the next 6 hours and a few such multi-step fine tuning, so we only ask the model to be good in short-term prediction. You roll it out, you also do well over long-term prediction. So the model is capturing the right characteristics both for the short and long term. And that to me is spanning these multiple scales that I showed you in the very first slide. That's very important for physical systems, right? And that's why this is very non-trivial as opposed to some of the standard machine learning that you may see. Yeah, so but in this case, the geometry information certainly helped in improving the stability. And we see this idea of incorporating geometry information very important in so many other areas as well. If you think about modeling and design in various cases of engineering, in this example, you want to understand the aerodynamics on the car. Is this a good design of the car? Is this aerodynamic? So there could be many different shapes. And for each shape, trying to get the data, then trying to learn a model based on the physics-based simulation is very expensive. So you'd rather have a model that generalizes across different shapes. And so one nice idea we came across was, how can we deform all the shapes to be, in this case, a donut, torus, but more generally can be, also in higher dimensions. But the idea is, once we can now go from different shapes to a standard shape in the latent space, we can come up with predictions, let's say, of pressure for aerodynamics, and then we go and deform it back to the shape of the car. So with this notion of like incorporating geometry information, but also the deformation of the geometry to handle multiple shapes, really helps us come up with good predictions. Again, nice ideas from optimal transport combining with data-driven learning. So the theme of like, thinking about how to add of information from geometry and physics really pays off in this case as well. So other examples of thinking about complex phenomena, fusion is an important one because the plasma can get very disruptive very suddenly. So the hot plasma inside the reactor can suddenly, get overheated. It can damage the reactor, and that's a big impediment to realizing sustainable fusion. And what we did was to train both on the camera data from the tokamak reactor. This is in collaboration with the UK Atomic Energy Agency, as well as the physics-based simulations, and be able to do this prediction not only accurately, but a million times faster than traditional simulations. So that means we can now take early interventions before disruptions occur, right? So if we can make these predictions now faster than real time, we can now do all these control policies to change the course of disruption and prevent damage of the reactor while sustaining the fusion. So having this balance is a big open question in fusion, and AI has really been able to overcome the cost of running complex physical simulations in this case. Many other examples like this. In this case, we're looking at quantum many-body simulations. They are perhaps one of the most expensive simulations to do, especially trying to do it classically, right? Like there's quantum systems that you want to simulate on classical computers, gets very expensive very quickly as you increase the size of the system. And the dynamics are also very difficult to model when we think about things like Mott insulators. And what we've shown is the ability to not only do it faster, but to extrapolate. So you train on smaller systems, and then you make predictions on much larger systems that would be too expensive for traditional simulations to even simulate. And that really is, to me, pushing that frontier, because you're training AI to do something that was not possible before. And so that's the aspect of what neural operators enable us, training on smaller systems and going to larger ones. And so many of this, what I showed you, was forward modeling, meaning we are learning how to predict the next time step in weather or the dynamics in these quantum systems. You can also ask about the inverse problem, where we want to simulate the system, but we want to ask what is the best design in some settings. For instance, with lithography, the challenge is being able to come up with a good mask design. Sorry about that. Good mask design, which has what we call the minimal violation. But the challenge is the small scales here, right, really matter. And so with AI, because it's differentiable, we can do inverse design as just gradient descent. So it can iteratively improve with every step. And that's what we saw here. If you saw these multiple epochs, we get over time, better mask design that would be too difficult for humans to have intuitions on how to do this. And that's even more the case when it comes to quantum systems, like in quantum dots. There's multiple gates that have to come together to pull the electrons, so very non-intuitive for humans to decide what is the best configuration. And we've seen very promising results on AI being able to do what humans were really having a hard time. And also in many other areas like nonlinear photonics. Again, for humans, anything that is nonlinear is not very natural. And we are seeing promising results with neural operators being able to design for things like pulse compression in these nonlinear systems. And over time, you can imagine much more complex chip systems that can be using AI at multiple levels. So this is at the level of physical systems. Now you can combine multiple such systems to also think about layout and others. Yeah, so that was like to me a quick overview of what AI can do for physics. Now, in terms of medicine, of course, you'll see over the next 2 days lots of different takes on this. I want to again focus on the physical systems, right? So, for instance, when it comes to medical devices, one example is a medical catheter. And I was surprised to hear that this is the most common healthcare related infections. So if you go to a hospital and if you're there long enough, you get a catheter, you're very likely to get a bacterial infection. And the reason for this is how it's really fluid dynamics. Bacteria tend to swim upstream near the walls of the pipe and go into the human body. And so, can we now come up with simple principles from fluid dynamics to prevent this? And what we thought of here at Caltech was to come up with a passive design where you 3D print small triangular shapes inside the pipe. And then, of course, the question was, what is the best such design? And the idea is those shapes not only make it harder for bacteria to swim near the wall, but they also should be creating vortices in the fluid flow so that it disrupts the flow even more. And so we had neural operators be able to learn the fluid flow, and then as an inverse design, you optimize the best possible shape. And this is the one that was 3D printed, and then our collaborators tried this out in the lab. And then you can see here that these are the bacterial particles under the microscope. They're all being pushed out. They're not able to swim upstream except for this lone one here. And even that's having a hard time coming into the human body. And here in this experiment, we saw 100-fold reduction in bacterial contamination. And in all these examples of design, what we see is AI is able to iteratively come up with an optimized design. And then the aspect of, in this case, 3D printing going to the lab needed to be done only once for validation. So this cycle of trial and error when it comes to physical experimentation, being able to thwart that and say, let's do more of those iterative cycles virtually and minimize what we do with the physical experiments. And let's say the physical experiments give us some feedback. We change our models as well, AI models to incorporate that. That's really, to me, the feedback loop, right? So an AI scientist is not only one that has these ideas at the high level, but that takes in the information both from knowledge of physics and from the experiments to come up with optimized solutions. And this is a great example of that. And in many other cases, when it comes to medicine, to me, diagnostics is an important one, and medical imaging of different modalities is an important inverse problem. Because we have no idea what's happening inside our bodies. We have like all these signals coming from different imaging systems, and how well can we come up with what's underneath, right? How much of a resolution can we get? How much of the tumor can we really image? That's the hard, challenging part. And in many cases, we can see not only speed up is important when we think about designing ultrasound for real-time, brain uh, imaging, right? Behavior decoding. So having higher speed is really useful here, but also like thinking about prior. So with data, we can have a better idea of what organs look like. So you incorporate that and you incorporate the physics together, you have a better idea of, more accurate idea of what the underlying organ is. So as just one example, what I want to show you is in ultrasound lung imaging, how we were able to change how the diagnostic is done. So as an example, with the current practice, what happens in lung ultrasound imaging is you don't look at the boundary, but you're really trying to study these blurry lines, what they call B lines, to see what is the aeration level in the lung. So it's very subjective, right? It's very hard to figure out what is the right approach. And instead, what we were able to do is come up with a full aeration map, and this improves the certainty of what people, even clinicians think is the right aeration level. And we can combine physics and real world data from tissues to have very accurate such aeration maps. So, as some of the examples in chemistry, I want to also see how multi-scale learning really is important. This was in the height of COVID, where we looked at not only modeling the coronavirus, but doing it at different scales. So, starting from the spike protein, where you look at how well it uh, you know kind of moves and what are the dynamics of it, to understanding like it's aerosol, so how it transmits. So this is a spanning many scales. And what we were looking at is, for instance, calcium ions in the respiratory aerosol, how well it binds with the spike protein. And this has a big impact on how infectious it is. And so that was a great effort of showing multi-scale modeling being important. And the AI we use there combined knowledge of physics by thinking about molecules not just as 1D or 2D, simple graph representation, but as full orbital systems with quantum effects, right? So having that knowledge of physics really helped train on small molecules, predict on much larger systems like thousands of atoms. As just to close this, there's lots of other areas where you can use the notion of AI. So I will let Arvind talk more about how you can model at the whole genome scale and come up with predictions, not only of the viruses we already know, but new mutations. Like in the case of coronavirus, we were able to successfully predict new variants of concern. And Francis will talk more about how we can use such a system that understands at the codon level different systems to also come up with new functional enzymes, and how we can do better in terms of both activity and versatility with the use of not only AI, but also the ideas from physics to have careful filtering of such predicted enzymes. So, but the other aspect of this is not only thinking about learning continuous systems, but also reasoning. I will not cover a lot here today, but just to kind of point out that if you want reasoning with guarantees, you need formalized systems such as proving theorems. And they're bringing this formal reasoning with continuous learning will make it a neurosymbolic system that will help us analyze both physical systems as well as predict and simulate on them. And so ultimately, all of this should come together. Yeah, so I'll stop here by saying I'm really happy to open this conference, and I'm looking forward to an excellent set of talks today and tomorrow as well. Thank you. So I think we'll go to the next session and we can have more questions during the break.